So welcome to week 12 of AI504. So this week we're going to talk about BERT and GPT, which are actually the extension of transformers. So if you want to understand BERT and GPT, you should already have a very firm grasp on transformers. So in case you have any question, actually there was a question about positional encoding on Classum. So I hope that my answer helped. And if you still have any question during this class, you can ask away anytime you want. All right, let's begin then. So a quick recap on word embedding. So we actually talked about how word embedding was static, and then BERT and ELMo were able to generate dynamic word embedding. So we'll talk about that a little bit. And then, yeah, contextualized word embedding. There's ELMo, which is the very first contextualized word embedding generator, and then GPT, which is actually not a word embedding generator. It's a language model. But they actually came about in approximately the same time period. So we're going to take a look at them all at the same time. Then came BERT, and then we're going to talk about GPT and GPT-3, and that'll be it. So hopefully we can end earlier than usual. All right, so word embedding. So we already know what word embedding is. We talked about word embedding and subword embedding and word2vec and that kind of stuff. So what the fundamental motivation for neural word embedding is that we don't want to express a word vector as a one-hot vector. We want to express it as a continuous representation so that cat and kitty are close to each other compared to cat and hamburger, which are completely, well, not completely, but like way more irrelevant than cat and kitty. So if words are represented as one-hot vectors all the time, then their difference is always, their inner product will always be 0, and their Euclidean distance will always be square root of 2. So no matter what word pair, as long as words are represented as one-hot vectors, their inner product always 0, their Euclidean is always square root of 1, square root of 2. So this cannot happen where cat and kitty are closer than cat and hamburger. That cannot happen as long as we're using this representation. So we want something better, which is what motivated all those neural word embeddings, and especially word2vec showed a very impressive performance, especially with the linear operation between words. So we especially took a look at skip grab, and we already looked at this. We're going to skip this one, and then came contextualized word embedding. So as a recap, I'll go through the scenario again. So the shortcomings or the limitation of word2vec is that you train a bunch of word embeddings, and then they're fixed. So when you want to use them, you have to just load them. You can just initialize your word embedding layers for your downstream task neural models, and that's it. So even though a single word can have multiple meanings, word2vec cannot really capture that, because, for example, here, if we want a word embedding, vector representation of the word stick, then there are at least 2 different words. Stick for like a long wooden object, or like a drumstick, or it could be like a sticking to a place, like a sticking to a person, like being attached to someone or being attached to a place. So there are at least 2 different meanings, and you can't, with word2vec, if you just retrieve a word embedding, stick embedding from word2vec, then that's it. So there's nothing really changes depending on the context, right? But here, so the very first dynamic or contextual word embedding generator, ELMo is actually a puppet character starring in Sesame Street. So that's actually it's a name of a model as well. So a user asks the model ELMo, what's the embedding of the word stick? Then there are multiple meanings possible. So use it in a sentence. So the user has to actually give a sentence. So let's stick to improvisation in this skit. So that's the sentence, or that's the context. So in this case, stick to is being used as a verb. So let's attach to, or let's keep things as original. So in that case, the embedding is yada yada yada. So we no longer just simply train word embeddings and then load them. We actually have to train a model that generates word embeddings, and then when in the downstream task, what we do is we load the model and then feed a actual sentence, like use it in a sentence, and then retrieve contextualized word embeddings. Right. So words have many meanings depending on the context, and ELMo is the very first one that actually, I'm not sure if it's really the first model, but it was the one that is probably mostly well known as the first work. Came about in 2018, so pretty long time ago actually. Word embeddings should be obtained on the fly depending on the context. So the model architecture looks like this. It uses at least 4 LSTMs. So actually, two for the forward and 2 for the backward. So it's bidirectional RNN. And each direction, it consists of 2 layers of LSTMs. So at least 4 LSTM cells are used in the entire architecture. And it's a rather simple architecture, actually. So you have words, you have, like I have a dog, well, yada, 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 something like that. So each EI, E1, E2, EN, they are all token embeddings. And then what you do is you simply just feed those token embeddings into the RNN, forward 1 time, backward 1 time. So it's bidirectional. And then what you do is you have the hidden layers from the top LSTMs, hidden layers here, 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 here. You have all the hidden layers. And then what you do is you can concatenate. As usual, you concatenate the hidden layers from both RNNs, both forward RNN and the backward RNN, and then you get the final contextualized word embeddings here. So, and the way that is trained is that it is trained via bidirectional language modeling. So, for this model, it is trained to predict the next word. Actually, it will be. So this word. So this one. Is trained to predict E2. This one is trained to predict E3, and so on and so forth. And the other way around, backwards, this one is trained to predict E n-1. The next one is trained to predict E n-2, and so on and so forth, right? So, and then you have the hidden layers from both forward and backward RNN. You put them together, and then that becomes your contextualized word embedding. So obviously, the same word stick can have different word embeddings depending on the context, because there are different neighbors or context words surrounding the word stick. So, and then you put them into the LSTM. So your final T's will change. Your final T's will change dynamically. So that's the whole idea. Oh yeah, and there's residual connection between layers, but that's just technical details. Right. So when you have a pre-trained ELMo, when you have already trained an ELMo model, and then you want to use them for downstream tasks such as sentiment classification, then how do you use it? So before the word embeddings and the word-to-vec and all that, what you would do is you simply represent your word as a one-hot embedding, and then you put them into the RNN. And then you take the last hidden layer, and then you put it through a sigmoid layer, and then you just simply do a binary classification, positive or negative, right? Positive or negative. But this is when you have nothing, when you just start from one-hot embedding. But when you start with word-to-vec, then what you do is you have a bunch of you have a dictionary of words, or it would be like a lookup table, and then each embedding or each column would be representing a single word. This could be like a, this could be boy, this could be cat, this could be dog, and then they're fixed. Once you've trained word-to-vec, it's fixed. And then what you do is in the downstream task, you initialize or you load the word embeddings from this matrix. You take a column from this matrix and then use them as your initial point for each word. So you no longer have to start with one hot vector, but what you do is you just simply use a word-to-vec vectors. So that's how you would use word-to-vec vectors in the downstream task. And this sometimes would give you a very a dramatic performance boost, but sometimes not at all. So it depends on what task you're doing, because if a task requires dynamic contextualization of words, then word-to-vec would not really help you a lot. But at least it would be better than one-hot embedding though, right? When you use ELMo instead, this is how you would use it. So instead of loading word embeddings, pre-trained word embeddings directly here, what you do is, instead of doing this, you're not doing this anymore. You plug in an ELMo model, Actually, maybe. You plug in the ELMo model, and then there will be a bunch of, then you put your E1s, E2s, E all the way to EN. So this becomes your input tokens. And then you would get a T1, T2, all the way to Tn, which are the contextualized word embeddings from ELMo. And then that becomes the input to your downstream task model. So there will be a downstream task model. There is still a downstream task model, but what is being fed is the output from the ELMo. It's no longer, you no longer start from word lookup tables. Where you start is you start from ELMo, and obviously ELMo's output would be the input to your downstream task model. Yeah, still need a downstream specific layer. So that was the basic idea. And then actually it showed a pretty good performance actually. So pre-training on 1 billion word dataset, there's a word dataset called 1B word. And when ELMo was trained with bidirectional LSTMs, 2 layers each, the forward language modeling perplexity was about 40. So perplexity means that out of like 50,000 different words, out of 50,000 different English words, you can narrow down the next word given the context within like 40 candidate words or something. So that's kind of the idea of perplexity. So when ELMo was being trained, the forward LM perplexity was about 40. So that's a pretty good performance, right? Out of all the words in the dictionary, you can narrow down your next word. For example, I have a dog and you have a slot. You have a blank. Then what would be the blank be? Then you can narrow down the candidate of the blanks into 40 words. That's basically what perplexity is. So simply adding ELMo to the baseline model gave state-of-the-art performance. That was back in 2018 then. So just simply, you leave the downstream task specific layers, you leave them alone. What you do is you simply plug in ELMo layer beneath them, underneath the downstream task model, and then you fully fine-tune the entire thing. And then you already have a state-of-the-art performance. Yeah, you fine-tune the language model using downstream test dataset. So you still have to fine-tune ELMo, actually. Right, and then you can see that, previous SOTA is all here. There's Squad, SNLI, SRL, core reference resolution, named entity recognition, SST. They're all very popular NLP task-specific dataset. Squad is question answering. This is question answering dataset. This is what? This is linguistic. This is language, natural language inference. Actually, I forgot the name for it. It's some kind of inference. Basically, you have 2 sentences, and you have to guess whether the first sentence is like one sentence entails another sentence or conflicts another sentence, something like that. It's a multi-class classification data set. Core reference resolution. We talked about how pronouns have to be resolved. Like the animal didn't cross the street because it was tired. What's the identity of it? Then the identity of it was the animal. So that's what core reference resolution is. NER, we know what. I think I talked about NER. It's basically trying to figure out in a sentence named entities like persons, organizations, places, dates, times, that kind of stuff. SST, I'm not sure what SST is. Anyway, so these were the previous SOTA performances, and they're the ELMo authors. They reproduced all those different models, and then, well, it didn't perform as well. Like originally the Liu et al., whoever this is, said that they had a squad performance of 84.4, but reproduction was 81.1. But at least when the authors of ELMo added their ELMo layer or ELMo generator, then you can see the dramatic increase from here to here, here to here, here, and here. So the increase is like at least like 3 to 4%. So pretty interesting, because the upper layer didn't change at all. No architectural change at all on the downstream task specific models. The upper layer didn't change at all. The only thing that changed is the lookup table. Instead of the lookup table, ELMo is taking its place, and you can see the already pretty big increase in performance. So the idea really works. It means the contextualized word embedding idea really works. Then came GPT-1 after ELMo, or actually, I'm not sure if it's after ELMo or approximately the same time. I'm not really sure. But GPT-1, so GPT-1 is, so ELMo was trained bidirectionally, and there was forward LSTM and the backward LSTM. GPT-1 has only forward with transformer instead of LSTM. So the title of the paper, or rather it's a report rather than a paper, is Improving Language Understanding by Generative Pre-training. So that is why it's GPT, Generative Pre-training, 2018, OpenAI. So it's simply just transformer decoder without encoder decoder attention, because it's just you only have a decoder, you don't have an encoder in GPT, and trained via only forward language modeling. And GPT-1 actually came out before BERT. So ELMo came out, then GPT-1 came out, then BERT came out. So that's the whole history. So you should already be really familiar with this whole architecture of encoder decoder transform architecture. And as I said in the previous slide, GPT only consists of this one. So only the decoder, and especially without this. So we don't need this. Because this encoder decoder attention is used for plugging in encoder output into the decoder when you want to do a sequence to sequence task, right? So we don't need this because we're simply just doing forward language modeling. We just want to predict the next word given all the previous words. That's it. So you only need masks. You still need mask self-attention because you're trying to predict the future word. So you cannot cheat. You can't do that. So you still need mask self-attention. Add and normalize, feed forward, add and normalize, and you repeat that for, I'm not sure how many layers that was. I think GPT-1 was 12 layers. So like 12 times 12 here. And then you have the good old linear and softmax layer. Oh yeah, here it is. It's 12 layers. So it's exactly the same architecture as BERT base, 12 layers, and 768 hidden size and 12 attention heads. So in all, it's about 110 million parameters. And it was pre-trained on a data set called book corpus. So it's like what? It's like books that don't have the IP issues. That's what I think. So all the like very old books or all the public books, there is no like the rights issues. So you can take GPT-1 was trained on books corpus, and the forward language modeling perplexity was 18. So before ELMo's perplexity was what? It was 40. So you could narrow down the next word range into 40 candidates, right? So that was already pretty good. But now GPT-1 can narrow it down to 18. So it's already a pretty big performance boost, right? So imagine being able to narrow down, being able to guess your next word every single time, next word within 18 words. That's a pretty impressive performance, right? And the important thing is no more downstream specific architecture. ELMo had a specific architecture for different downstream tasks. For sentiment classification, you have sentiment classification layer. For squad, you had the question answering layer. Like each task required specific layers, and you just simply plug in ELMo layer beneath the task specific layer, right? In GPT-1, you don't have that actually. So what you do is you just have one more linear layer, and that's it. So you have 12 consecutive decoder, and then on top of that, you have a task classifier and text prediction. So for example, if you're doing classification, then on top of this 12 consecutive decoder, what you have is you have just a single linear layer because you're doing multi-class classification, binary classification. You just need one more linear layer on top of it. So that's it. For example, if you're doing a sentence similarity check, given two sentences, whether this sentence and that sentence is close enough or is far enough semantically, then you need two heads to predict, right? Because you have two sentences as input, so you need two heads to encode them and then do an inner product or whatever. So you have two heads. You have one here, another here, and that's pretty interesting. They put text 1 and text 2 in this sequence, and then text 2 and text 1 in this sequence, and then they have this pre-trained transformer. This is 12 times 12 decoder only, and then you have outputs from here, and then you concatenate them or you add them your inner product and whatever, and then you have a linear layer that says binary, like they're similar or dissimilar. So that's similarity check. And multi-choice questions, you have as many heads as the number of choices. So basically, you just reuse this 12 encode 12 consecutive decoder only architecture all the time for different tasks, and that's it. So that's simply it. And yeah, as I said, no downstream. So fine-tuning the entire GPT with supervised labels for downstream tasks. So if you're already familiar with GPT-3, you know that GPT-3 is only a zero-shot only model, but in GPT-1, it was not such like that. You had to still fine-tune GPT-1 for downstream task specific performance. Yeah. So downstream task inputs are all converted to a sequence of tokens, whether it's a question answering task, whether it's a sentence similarity task, whether it's whatever. It's always, you have to convert to a sequence of tokens so that you can put them into this decoder only architecture. All right. So compared to, there are some specific supervised models like these for different tasks, like NLI, sentence inference. This another inference. This is, I think they're all like inference tasks. Like what given two sentences, whether one sentence is entailed from another or their conflict another or something like that. So at least on their table, performance looks good on GPT-1, but it's the task is pretty constrained though. It's only like language inference tasks. This is, I think this is a story close. These are kind of like questions. They're not questions, right? The story close is probably like fill in the blanks kind of task. And in this case, they still had a pretty good performance, but these are rather unknown models actually. So I'm not sure. This is all back in 2018, so we didn't pay too much attention to GPT-1 and how it was. Nobody thought it was like the best model out there, or it didn't make any big changes, because right after GPT-1 actually came about BERT, which actually made a lot of difference in the NLP world. Right, they actually did a lot of different tests: classification, semantic similarity, glue, and all the time they claimed a good performance. But again, this was back in 2018, and the performance might not look as impressive as these days. Right. Yeah, back in when GPT-1 came out, and then BERT was coming out, BERT was in the oven, and then ELMo came out. Still, like transformer was not the go-to model. LSTM was still the basic model in the NLP world. You can see like all these different LSTMs and ELMos and these kind of stuff. So LSTM here. So LSTM still had its place in NLP, but then a couple of years later, nobody is actually using LSTMs or RNNs anymore. They're all using transformers. So this was all back in 2018, like very old story. All right, so that was GPT-1, and then GPT-1 would evolve into GPT-2 and 3, but we're going to talk about it later. So we're going to divert a little to a BERT. So BERT came out after ELMo and GPT, and possibly inspired by ELMo and GPT, because they had a picture in the BERT paper. I'm not sure if it was a BERT paper or the BERT slides, their presentation slide, but they had this picture where this is theirs, this is BERT. So this BERT was developed by Google researchers. So BERT is theirs, and then there's OpenAI GPT, and then there's ELMo, and this is how they're different from the other similar works. So ELMo is a contextualized word embedding generator, and it consists of forward and backward LSTMs. OpenAI GPT is only forward-only model, and actually, before GPT-2 came out, GPT-1 was still designed to generate word embeddings, not like sentence generator or like a zero-shot task performer, nothing like that. GPT-1 was still inspired by ELMo, because ELMo is a word embedding generator. It's a dynamic word embedding generator. GPT-1 was also motivated to be a word embedding generator, and so is BERT. So how is BERT different from the other two? So first of all, BERT is bidirectional, like ELMo. ELMo is bidirectional, right? ELMo has this forward and backward. So BERT is also forward and backward, because it has a full attention everywhere. And the difference between BERT and ELMo is that BERT consists of transformer layers and ELMo consists of LSTM layers. How is BERT different from OpenAI GPT? Well, obviously, GPT is unidirectional. It only goes this way, only goes this way, only goes this way. And BERT goes both ways. Well, actually, BERT has all the ways because it's fully attentional. It has full attention. So everything attends to the other, everything else. So it's fully connected. So that's how BERT was different from OpenAI GPT and ELMo. Yeah, takes the best of two, bidirectionality and powerful transformer. So this was back in 2018. So 2017 is when Transformer came out, and 2018 is when BERT came out. So BERT, actually in 2018, a lot of things came out. So BERT architecture is simply just 12 layers of Transformer, but the way it is trained, or these days it's called self-supervised learning, but back in the day, I'm not sure if it was called like that, but back in 2018, BERT was trained without any labels, so that's probably why people call it self-supervised learning. And the way that it is trained is, well, the input is a little bit different from the original Transformer. And the input is token, there are token embeddings, just like BERT, and just like Transformer. There's token embeddings here, and there's subword embeddings, obviously. There's positional encoding, just like sinusoidal positional encoding that we talked about. And then there's one more thing. There's something called segment embedding. And why do we need this? Because BERT is trained with two sentences all in the pre-training stage. BERT is trained with two sentences always two sentences, like here, one sentence here, my dog is cute. Another sentence, he likes playing. And then to separate the two sentences, there's some special token, special word, or some special token called separator. This is a separator. So this separator has a place in the lookup table. In the lookup table, there are about 30,000 different subwords like my dog is cute. He likes. You can see the play sharp ing because BERT is using word piece subword encoding strategy. So there's play, there's ing, but they're actually just one word, playing. But it is separated into two parts, play and ing. So ing has its own place in the lookup table, play has its own place in the lookup table. And then again, as I said, separator, or actually is sep has a place in the lookup table. And then there's CLS token, actually. Actually, sep is used one more time as a termination symbol. So there's one termination symbol for the first sentence, another termination symbol for the second sentence, and then there's something called CLS, which is also a special token that has a place in the lookup table. So CLS, we're going to talk about what is used, why the purpose of CLS. But basically, CLS is a special token representing all inputs, because there's first sentence, there's second sentence, and sometimes you want to use both sentences at the same time. If you want to do like a sentence similarity check or like inference check, then you need to have a single token that represents all two sentences. So that is when CLS is used. So that's why segment embedding is used, because segment embedding kind of like indicates the first sentence. You can see the EA here, and then the second sentence, EB. That's it. So you have just two trainable embeddings, EA, and EB, and that's it. And they're used just as a one more summation to token embeddings and position embeddings. You just add segment embedding one more time before you put the sum. The sum would be like this. This would be the sum. You plus, and then you get this. You have the input, and then you put them into a bunch of transformer up on the and it would consist of 12 layers of transformer layers. So that's it. Question from Mindoki: are segment embeddings also added? Yeah, they're added. So token embeddings, position embeddings, segment embeddings, they're all added. And why they need to be trainable? Well, what are you going to use them? What are you going to use as segment embeddings if not trainable? Then, well, it could be one hot vector, but it wouldn't make much of a sense if you use one hot vector, because if you think about it, this would already be like what? This would be 768-dimensional vector. This would also be a 768-dimensional vector, because you need to sum them up. Then this also needs to be 768-dimensional vector, because you need to sum all of them up. And you have to initialize EAs and EBs with something. and you don't want to use one hot embedding, then either it would be like 0, 1, like 1, 0, 0, 0, 0, or for the EA, and 0, 1, 0, 0, 0 for EV, which would not be very informative. So you leave them as you randomly initialize, and then you leave them as trainable parameters, and then you backprop, and then they will be trained along with the token embeddings. Does that make sense? Great. So how you train it? So BERT is what you want to do with BERT is the purpose of BERT is to generate well represented contextualized word embeddings, right? Because all these models, ELMo, OpenAI GPT, BERT, they're all contextualized word embedding generator. Like it's completely different from word2vec, as I said. It's a contextualized word embedding generator. So how would they train their models, ELMos and GPT and BERT? How do they train their models to make them a good contextualized word embedding generator? ELMo trains them with forward LM and backward LM. OpenAI trains it with forward LM. BERT, how would they? It's a fully connected attention layer. So you cannot use forward or backward language model, because then you have to use masked self-attention. So you can't do that with BERT. BERT has to come up with completely different training strategy to make it a good contextualized word embedding generator, right? So there's where the brilliance of the Google NLP researchers really shine. It's that they randomly masked the identity of words and then let the model guess them. So for example, they mask 15% of the input words, or input tokens, actually, input tokens, put them into and so the other segment embeddings and position embedding would be intact. They are left them as is. And this token is replaced with something called mask token. So mask token is another special token that has a place in the lookup table. So there's actually 3 special tokens. There's CLS, there's SEP, and then there's mask, right? And what you do is you randomly select 15% of your token embeddings, you replace them with mask token, and know that they're the same mask token. They're the same mask token. They're using the same lookup index. And that is okay because we have position embedding. So they're distinguished. These two are distinguished because they have position embedding. So they're not the same mask. They're different masks in different positions. So your final input to the transformer layer, so there will be a bunch of transformer layers here, right? Transformer layer, 12 times. You put these pink ones into the model, and then you would have corresponding contextualized output after 12 layers, right? And the task is that you have to guess. Oh, actually, okay, so I don't have. Yeah, sorry, I don't have that picture. Actually, I should have. Let me draw the picture a little bit better then. Right, to make it more visible. So there's 12 layers of transformer times 12, and then you have the same number of tokens, contextualized tokens here. You know this is SEP, you know this is CLS. You have something that you don't know is cute SEP. He likes play, something that you don't know. So after the 12 layers of transformer, you have this as an output. You have these as output. And the task of BERT training is, the objective BERT training is that, guess what this is? And guess what this is? You put a mask, so you don't know its identity, and you're asking the BERT model, or actually 12 layers of transformer model, to guess its identity. And for some masks, it's extremely easy to predict, because, for example, if you look at here, he likes play and what? It has to be, at least it cannot be like, it has to be something that makes this sentence a grammatically correct sentence, right? So it probably has to be sharp ing, because sharp ing, so making it as he likes playing. He likes playing is a grammatically correct sentence. Anything else would easily break the grammaticality. I'm not sure if that's a word. So there's very small number of candidates that makes this sentence a good, like a legitimate sentence. So in this case, guessing this correctly could be a bit easier compared to here. What would this be? Because this could easily be something else than dog, because all the hints that we are given is that it is cute and it's a he and it can play. So it could easily be a son or friend or cat. It could be anything else than dog. There are a lot of different candidates. So, but if like BERT, you look at a bunch of text, like I think BERT was trained on Wikipedia and book corpus at the same time. So if you look at as many articles as BERT, like if you read all the Wikipedia, if you read all the books, all the things in the history of humanity, then you know that compared to friends, dog is probably more likely to come here, like probabilistically or statistically. If you look at all the words, if you look at all the texts, all the articles, all the books, all the news articles, all the Wikipedia articles all the time, then you know that there's a statistical difference between different word candidates. So that is why BERT can actually re-identify the mask tokens pretty accurately. I think the mask token perplexity was about 11 or 12 or something. So way better than way better than ELMo and GPT. So that's it. That's what BERT basically does. You just randomly mask out 15% of your input tokens, and then you ask the models to guess the identity, and that's it. And it doesn't require any human annotated labels, because you're just simply removing the thing that was there, and then try to replace it, and then try to restore it. So you don't need any human annotations at all. So it's a pretty cheap operation. Question from Park Seok-Bwan: why is BERT using 2 sentences as an input, not 1 or 3? So good question. We will actually see, because short answer is that because many downstream tasks in NLP require 2 inputs. If it's question answering, you have a article and a question. If it's a sentence similarity check, then you require 2 sentences. If it's a language inference, you still need 2 sentences. It's usually 2 inputs at the same time. So that is why BERT is trained with 2 sentences. And that is why there's another task that's something called NSP, Next Sentence Prediction, NSP. So this is first one. This is called MLM, Mask Language Modeling. Very, very important. Very, very, very important. MLM, very important. Mask Language Modeling. This is the first task. NSP is the next task. And NSP is basically, you're given 2 sentences. So what you ask the model is, you use the CLS, which is the representation of 2 sentences. You take the CLS token. Well, actually, there should be like a transformer here. There's transformer times 12. Then there's CLS here. You take the CLS. There's a bunch of tokens. You take the CLS here, and then you have binary classification, 1 or 0. 1 being that these 2 sentences are consecutive. That is 1. 0 being that these 2 sentences are not consecutive. So during training, you would sometimes put completely irrelevant sentence in the second slot and then ask the model to predict 0 correctly. So that's what NSP is. And it turns out that NSP is not as important as MLM. MLM is the essence. This is the essence of BERT. NSP, not so much. But it says it's helpful for some downstream tasks, but I don't think people use NSP these days. Right, so there was a question from Yimin-seung. Can BERT generalize to more than 2 sentences? Probably no, because it has only seen SEP tokens twice, and it has never seen another sentence after the second SEP token. So I'm not sure how you can't guarantee how BERT will behave in the inference stage when you put more things after the second SEP. Hope that answers your question. So my answer would be probably no. So downstream tasks on BERT. Oh, right, yeah. BERT was pre-trained on books corpus in English Wikipedia. Oh, and the LM perplexity was 4. Sorry, it wasn't 11, it was 4. So when you put a random mask on any word, and then you ask BERT to guess its identity correctly, then BERT can narrow down into 4 candidates. Out of 30,000 subword candidates, it can narrow down into 4, which is super accurate. And just like GPT-1, BERT base has 12 layers, 768 hidden layers, hidden size is 12 attention layers. So all in all, 110 parameters. Right, and different input output for different downstreams. And actually, this is pretty natural. So when you want to perform different downstream tests with a pre-trained BERT model, you have to fine-tune BERT actually. So, and since each downstream task has different input formats and output formats, you have to, massage the input output specs a little bit. So if you're doing, like sequence tagging being like NER or part of speech tagging. We talked about what sequence tagging is, right? There was 3 different tasks in sequence related tasks. There's like sequence level classification. Then there's each token. You do a classification for each token, and then you have an encoder and decoder, right? If you remember, if you have a sequence, you put all the sequence into the LSTM, and then you take the last one, and then you do a classification. That's number 1. You have you have a sequence, you put them into the LSTM, and then you do a classification for each token. That's number 2. And then you have encoder and decoder. That's number 3. And sequence tagging is basically this. This is sequence tagging. So if you want to do sequence tagging with BERT, then actually you don't need 2 inputs. You only need 1 input because you're given 1 sentence and you want to do like a part of speech tagging, or you're given 1 sentence and you want to do named entity recognition. Then you don't need 2 sentences. You don't need the second part, right? So what they do with BERT is that they put text and pad. So pad is not actually, it's a 4th special token. So you have 1 sentence like I have dog sep, then pad. Actually, I'm running out of space. So let me do that again. So you have I have dog. Well, there should be CLS. Then there's sep. Then there's pad. Then there's sep. Oops, sep. And this becomes your input to the BERT. And then the output would be also this here: 1, 2, 3, 4, 5, 6, 7, 8. And you basically want this to be what? Is it a pronoun? Yeah, I is a pronoun, right? So yeah, this should be pronoun. This should be have is a verb. You want this to be article. 부정관사죠, article. Noun. You want this to be noun. Something like that. So that's basically what you do. How you perform POS tagging, part of speech tagging with BERT. You have 1 sentence and a pad, and then you take the first part, and then you have a classification model running on top of each token. So that's how you would do sequence tagging. For text classification, it's the same thing. If you want to do a text classification, you have, let's say that you want to classify whether this, so this is the same input, and what you want to do is you want to classify whether this is a positive sentence or a negative sentence, text classification, whether this is positive sentence, negative sentence. You have, as again, same, you put this into BERT, and you have 1, 2, 3, 4, 5, 6, 7, 8 outputs, and you take the CLS, which is actually the representation of the entire input, and then you have 1 or 0, which is positive or negative. So that's how you do a text classification. Paraphrase detection is whether 2 sentences are the same thing. They mean the same thing. Then you actually need another sentence. I own a dog, sep. And are these two the same? Then you have sep, I own a dog, sep. Then you take CLS, you do a 1 or 0 binary classification. 1 being they're the same thing, 0 being they're not the same thing. So that's CLS, a linear classifier. So that's how you would use or fine-tune your pre-trained BERT. You have to massage your inputs a little bit to make it compatible with the BERT format. So that's a little bit of manual labor goes in, but that's nothing compared to how much performance gain you can acquire from the BERT pre-trained model. So that's it. And BERT actually showed a pretty impressive, not just good, but very, very impressive performance, because it showed if you look at the previous performance, like here, these are all different types. So I think this is glue benchmark. Yeah, this is a glue benchmark. Glue benchmark is a data set consisting of like 10 or 12 different NLP related tasks, like question answering, inference, paraphrase detection, yada, yada, yada. There's a whole bunch of different tasks. Oh, actually, it's not 12. It's like 1, 2, 3, 4, 5, 6, 7, 8. 8 tasks, I think. 8 tasks. And if you look at the performance between the BERT and the previous SOTA, you can see the dramatic increase. For example, here, previous SOTA, pre-OpenAI, so before GPT-1 came out, SOTA was 35, and then GPT-1, 45, then BERT, 60. You can see the dramatic increase in the performance within a year or two. So here as well. And the average performance is like whopping 8% at 8% point, which is just, and you can see and the important thing is that BERT doesn't have a task-specific layer like ELMo. It still uses only 12 layers of transformer and one additional linear layer for the task-specific logic generation, right? So that's it. It's just 12 layers of transformer with one linear layer, and that's it. And with that simple architecture, 8% average performance increase. So you can see the shock that people must have felt when they saw this paper. Question from Kim Yujin: do we full fine-tune BERT for downstream tasks, or do we use? Yeah, it's full fine-tune. It's full fine-tune. You have to fine-tune BERT for every single different downstream tasks. You can try linear probing, but it wouldn't be as impressive as this. Cool. Right, and squad also just impossible performance increase, because before BERT came out, the best performance on squad data, which is question answering data set from Stanford. Actually, it's Stanford question answering data set, squad. So before BERT came out, BiDef is what actually it's a model that was developed by Professor Seom-In-Jun from our school, actually, BiDef. So if I remember correctly. So that showed the best performance, but then BERT came out, and then BERT actually showed like impossible performance, like 90 whatever. And you can see that the human performance is around 91 and 91. And BERT is showing better than like superhuman performance. Squad 2, similar performance. Human was 89. Oh, actually BERT large is 83. So at least BERT, back in 2018, BERT wasn't able to outperform humans for squad 2, but now these days, actually, it outperforms. So what is squad? Let's take a look at the squad a little bit in more detail. So squad is a question answering data set, Stanford question answering data set, consists of about 100,000 different questions. And it looks like this. There's a text. It's just like 수능 언어 영역. So there's text, and then there's question. And the answer to the question is always within the article. It could be a single word, or it could be a span of words, but at least it's always within the article. So the task for the thing that the model has to do is digest these two, article and the question, accept those two sentences, two text, and then find the span within the text, which has to be the answer. Yeah, so the answers are segment of text from the passage. We call this a passage. 지문을 passage, and it has a bunch of different types of questions. It could be like date related, numeric related, person related, location related, all different kinds of questions. And the squad point, this is squad 1.0 or 1.1, 100,000 questions, and squad 2.0 adds 50,000 unanswerable questions. So some questions you can't just answer with the given passage. For example, here, if you read this, and if you try to answer this question, what was the name of the 1937 treaty? There is no answer to that. It doesn't say anything about 1933. 1933 treaty, but the model is actually being confused and answering with this wrong answer here because this is 1940 treaty name, and the question is asking for 1937 treaty name. So the model is being confused. So the model, so from starting from 2.0, the model has to be able to answer no answer. So there's always this one special class that says no answer, which means that it doesn't know. So either the model has to find the span within text, within the passage, or it says no answer. Right. And the way that the squad dataset, the performance is measured is either exact match, which is that you have to match exactly like this. For example, if the answer is within a cloud, then you have to exactly get 3 words correctly, or your span has to start from here and end here and here. That's exact match. That's exact match. F1 measure is you give partial scores to, like, partial span. For example, if you answer a cloud instead of within a cloud, then you get 2 out of 3. 2 out of 3. So based on two measures, this was pretty. I think this leaderboard I took this leader from like last year, I think 2021 or no, actually 2020, probably 2020. Yeah, right. Human performance, as I said, is an 89 for F1 score and 86 for exact match, and you can see that already. Some model is outperforming. Actually, most models, all models are outperforming human performance. And you can see they're all probably a bunch of BERT-based models, like Albert. Albert is another BERT variant. There's Albert, Electra. Electra and Albert, they're both BERT variants. Also, again, Electra, Albert. Not sure why Albert is on here. And then, not sure what SANet is. Not sure what this is, but at least probably it's some self-attention related architecture, probably. So you can see that all superhuman performance is enabled by BERT variants. So that's how you can imagine how powerful BERT is. Before BERT, nothing came even close to human performance, actually. And because LSTM is such a limited architecture, because it has such a strong inductive bias of the order, the concept of order is embedded into the model itself. So, but compared to but transformer doesn't have any restriction. It's just fully connected. Everything is connected to everything else. So that's where the power of transformer really kicks in. It's the set encoder, as I said last time. All right. So how do we? So just a bit more detail into squad. So how do we fine tune squad? How do we fine tune BERT for squad specifically? So as I said, squad requires 2 inputs, which is one passage, another question. So here, there's a question, there's a passage, and this is just an example I took from this very nice YouTube video. The passage is that BERT large is really big, yada, yada, yada. So it's a bunch of description about BERT large. And the question is, how many parameters does BERT large have? So the answer is 340 million. So 340M, that's our answer. And if you tokenize it with word piece or byte pair encoding using subword encoder, then you have a bunch of tokens, basically. And you put question first and then reference later, passage later. You've already pre-trained your BERT with 2 sentences, sentence 1, sentence 2. So question takes sentence 1's place and passage takes sentence 2's place. And then you fine-tune your BERT. And obviously, this is your segment embedding, EA and EB. And you have CLS and SEP, and there should be another SEP here at the end. And so you have this, and the answer, the way you fine-tune BERT is that you need to find the span of your answer within the reference, right? Within the reference, because the answer is always within the passage. So what you do is you try to guess or predict the the starting place of the span, which is where? Which is, this is your answer. So this should be your start. And this should be your end, right? So you have to train your model to take the output of 340. This will have a contextualized output right here, right? After 12 layers of transformer. Here, you have to take this one and make a binary prediction, 1 or 0, 1 or 0. And this particular token, output token should be predicting 1, and all the others 0, 0, 0, 0, 0, 0, 0, because this is the start. And the same goes with end. So it's a span. So you only need a start and end, right? You need the beginning and the ending. So the end should obviously be M. So with all the binary classification, again, another binary classification, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, like all the other. This should be the one with 1. All the others should be 0. Like it should be 0, 0, 0, 0, 0, 0, 0, 0. Like this is your ending token. So this should be your 1. So it means that when you fine tune your BERT for squad type of data set, you need 2 prediction heads, one for start span, one for end span. Right. So this is actually what you get after you fine tune your BERT. So this is your question. So this is the actual performance of fine-tuned BERT for that exact same question passage pair that we've seen. So how many parameters does BERT have? BERT large have? SEP. So this is your question. And this is your answer. I'm sorry. This is your passage. This is your question. And the answer, the starts, so the model, where did the model predict to be the start span? Then you can see here, it's way here, which is exactly here, 340. So pretty clear distinction between all the other words and the start span. But when you go to the end span, end prediction, it's a bit confusing. So let's see that where the model actually thought that the end prediction could be. So there are 4 candidates being anything within here. So, right, if you go here, you see that. So the model said that it could be starting from 340 and end. Why can't I scroll it here? Okay. So it could also end here, which means that the answer is 340 instead of 340 million. But if you think about it, 340 is also a legitimate answer because the BERT large could have 340 parameters, not 300 million parameters. So that's also a legitimate answer. But of course, the highest score was given to 300M, which is M here. So the correct answer is actually 340 million. But then the second largest logit was given, the second highest logit was given to what? Given to 340 parameters. So actually, if you answer how many parameters does BERT large have, then 340 parameters is also a good answer. And actually could also end with a exclamation mark as well. So these are all good answers. Like these are all good answers. So that's why BERT is probably being confused between these 4 candidates. All right. So it's doing a pretty good job. So hopefully you understand how you can pre-train BERT and then fine-tune BERT for your own specific task, downstream task. For any downstream task you want, you can fine-tune BERT by simply manipulating your inputs a little bit. Just remember that it always has to be 2 inputs, either as input and pad or input and input, right? Okay, so we're going to move on to GPT-2 and 3 now. Any question regarding BERT so far? Question from Imin Sung. Why BERT predict start end position isn't enough to predict mass tokens as answering? You mean for a squad? I don't know. Where would mass go here? You are given a question and a passage. Where would mass go? 그러니까 지금 질문 여기에 마스크를 넣는 건 이미 치팅 아닌가요? 여기에 마스크를 넣는 거는 이미 여기가 답이라고 알려주는 거잖아요, 사람이. 그러니까 인풋에다가 이거를 340M 대신에 마스크 넣으면은 모델한테 여기 정답입니다 하고 알려주는 거잖아요. 혹시 이해되시나요? 제가 하는 말이? 네. 그러니까 마스크를 주면 안 되겠죠. 마스크는 프리트레이닝 때만 쓰고요. 그 다음 모든 다운스트림 태스크 때는 원래 있던 라벨을 씁니다. 원래 있던 슈퍼바이즈 라벨이 있겠죠. 그러니까 스쿼드도 다 라벨이 있어요. 이제 모든 질문과 모든 패세지와 질문 셋에는 패세지 안에 이 질문에 대한 정답이 있거든요. 그 시작과 끝점을 항상 데이터 안에 있어요. 매 그 질의응답 쌍에. 그럼 그걸 보고서 버트를 이런 식으로 이제 파인 튜닝을 스타트에 대해서 한 번, 엔드에 대해서 한 번. 사실 한 번씩 한 게 두 개를 동시에 하겠죠. 두 개의 리니어 헤드가 있는 거니까. 를 가지고 이제 파인 튜닝 하는 겁니다. 마스크는 쓰지 않아요. 파인 튜닝 때는. Good question. Could be confusing. All right, gonna move on to GPT-2 and 3 now. So GPT-2 came about in 2019. So GPT-1 came out in 2018, and then they saw like some kind of potential, and they blew it up in scale into something called GPT-2, and their title is still a report. It's not a like a peer-reviewed paper. They were still working towards something larger than GPT-2. So the paper is called language models are unsupervised multitask learners. And it's 10 times larger than GPT-1. So GPT-1 was what? GPT-1 was 110 million parameters. So 이게 1억 천이죠. 1억 천만인데 이게 15억이 됐다. So 이제 10배가 커졌다 이겁니다. So it's become 10 times larger than GPT-1. Instead of 12 layers, now it has 46 and 48 layers, 1,600 hidden sizes, and context-sized 1024 tokens. So instead of, I think BERT GPT-1 and BERT base, they only supported up to 512 tokens, but now GPT-2 supports 1024 tokens. And they trained on web text, something called, they no longer, so GPT-1 was trained on book corpus, but now GPT-2 is trained on something called web text, which is way more larger than books corpus, probably. And their forward language model perplexity was 10 to 11. So before GPT-1's perplexity was 11 point something, right? 11 points something. So it was 11 basically, but now, sorry about that. Not 11. It was 18. GPT-1's perplexity was 18. Now it's decreased towards 11, which is way more. It's a dramatic, explosive increase. So it will be a decrease actually, 18 to 11. It's a dramatic performance boost basically. And yeah, so web text is what? Web text is outbound links from Reddit post. Reddit이 이제 그 미국의 막 약간 그 뭔가 우리나라 지금 뭐 DC 인사이드나 뭐 그런 데죠, 레딧이. 그래서 어떤 커뮤니티인데 거기에서 이제 외부 링크가 걸려 있는, 그러니까 외부 링크가 걸려 있다는 건 이제 의미가 있는 훌륭한 글이니까 외부 링크가 있겠죠. 거기서 이제 다 긁어와가지고 삼카르마 이제 뭔가 삼카르마 약간 뭐 좋아요 이런 거죠. 이제 썸즈업 같은 건데. 그러니까 이제 레딧에서 좋은 그 썸즈업을 추천을 받은 글들 중에서 외부 링크가 있는 애들은 전부 다 긁어가지고 한마디로 이제 인터넷에 있는 많은 다양한 걸 긁은 거죠. 그래가지고 40GB 텍스트를 얻었다 하는 거고, 일부러 위키피디아 뺐대요. They excluded Wikipedia specifically because a lot of benchmark tests on the downstream test include Wikipedia articles. So they wanted to prevent their model from cheating. So they wanted to separate the training set and the training samples and the test samples. So that's why they excluded all Wikipedia articles on training GPT-2 or pre-training GPT-2. And the important thing is they only perform zero-shot tests. So zero-shot thing was a big thing starting from GPT-2. So GPT-1, we saw that it was fine-tuned for each downstream task, right? But starting from GPT-2, no fine-tuning at all. It's just zero-shot test, zero-shot. So how do we do it? How do we perform zero-shot with GPT-2? Because GPT-2 is nothing more than just a language model. It's still a language model. Nothing changed from GPT-1. It's that only the number of layers increased, and that's it. And actually, they're using a larger data set to train, but it's still forward language model. You're just trying to predict the next word given all the words so far. Still, nothing really changed. But how do we perform zero-shot tasks? So we need to tell GPT-2 what kind of task we want it to perform, right? So how do we tell it? How do we tell it? that is the way they do it is they use something called, well, these days we call it prompts, but they call it textual input or condition, textual condition for specific tasks. So for example, if you want the GPT-2 to perform summarization, then you condition, this is called prompting these days, or priming, but this is, you condition your model, your pre-trained model with a few examples, and then start sampling tokens auto-regressively. For example, you want to do summarization, then you put long text, and then you put something, some special indicator. It's not a special token because TLDR is still, TLDR would be, it would be tokenized into TL semicolon DR, like TL semicolon DR, they would have their own subword encoding, right? So you put TLDR, and then you put the correct summarization, and then you repeat it n times, and then you put the next time, long text, TLDR, and then you go. That's where the GPT-2 will actually start sampling the next words or next tokens. And hopefully we want this to be the actually good summarization of this. Because you've already demonstrated this pair, long text summarization linked by TLDR, which is a special indicator. You've already shown them n number of times as example, and then you expect the GPT-2 to have picked up the pattern and then do exactly the same thing. For translation, you could do the same thing. For translation, English to French, you have English sentence, you have French sentence, you have a link between the two, which is simply just equal sign. And then you repeat it n times. Then next time you put English sentence, equal sign, and then go. Start sampling, auto-regressive sampling. And then hopefully you want this to be the correct translation of this English sentence. And actually, surprisingly, this works. Actually, I'm not sure if we can call this zero shot because you're showing examples here. You're showing examples n times here. So it's not exactly zero shot, but it is zero shot because you're not updating the parameters of GPT-2 at all. You're just reusing, you're freezing the parameters of GPT-2, and you're just reusing it by showing examples, showing a few examples. So that's what the power of GPT-2 is. Right, so weirdly good. Weirdly, people just didn't realize why it was so good, but weirdly good zero-shot performance on multiple NLP tasks. No fine-tuning, means no modification of the GPT-2 pre-trained parameters. So a bunch of different tasks, and I think they're all language modeling tasks here. So Lambda, I think these are all different bunch of corpuses, and they're all language modeling tests, meaning that you want to predict the next word given the previous words. And you can see that the state of the art. I'll actually, I'm not sure people use these data sets very often, but at least 1 BW, 1 billion words, or Wikitext or English Wiki 8, they're like pretty widely used corpus for pre-training purposes. And you can see that their GPT-2's downstream, GPT-2's zero-shot performances as well as state-of-the-art, like here, 9.00 compared to 9.93, 28.8, not so much here, though, and 18.3, 17.48. So we can see that without any fine-tuning, GPT-2 can show a very, very good performance, like as good as state-of-the-art or slightly underperforming compared to state-of-the-art. And this is different things. So these are all language modeling tests. These are all language modeling tests. There are different tasks, such as reading comprehension, translation, summarization, question answering. And you can see that for some tasks, GPT-2's zero-shot performance is very, very impressive, but some not really, not much. So, for example, question answering. I think this is not so. This question answering is not. It's not squad. It's called open domain QA system, which means that you're given a question without a passage. You're just given a question, and you need to search all the passage in your database and then answer the question. So that's what open domain QA system is. So in that case, how does GPT-2 perform compared to the state of the art, which is around here, GPT-2 can perform zero shot about 44%. I'm not sure if it's 40% or 4%, but there's like a large gap between the two. So GPT-2 is not, it's not a magic box that can perform everything as good as supervised models. Like summarization as well. Like summarization, the best performing model is like up here, but the zero shot model is down here, which is better than random. Translation. So these are the unsupervised statistical MT, which means that they're all unsupervised. Like this, like all probably unsupervised, meaning that they didn't use any supervised paired corpus. But compared to unsupervised statistical MT, which is specifically trained or unsupervised manner trained for translation, compared to that, GPT can perform. Like there's a gap, but still it's pretty impressive. So yeah, so still like in a lot of different tasks, except for the LM for a bunch of different tasks, GPT-2 has a potential, but is not as good as state of the art. Here, there's also some gap here. So it means that, well, something interesting is happening with zero shot, but it is not as good as supervised state of the art models. So that's basically the message that GPT-2 is sending out into the world. Right, and well, at least it's good for language modeling. So which means that it is very good at writing things. So for example, here this is a text given to the model, and then we ask GPT-2 to finish the article. So this is kind of like the title or like abstract, and this is the main text that GPT-2 wrote, and you can see that this is already very, very like high quality writing. So if you read this part, it means it's about something called discovering a herd of unicorns in the Andes mountain, which means that it's completely fake. Like there is no such thing. This is completely new, fake, unexisting text that people just wrote for testing GPT-2's capacity. So when GPT-2 is writing this, it is not memorizing and then just copy pasting from its parameters. It's actually really generating based on this completely fake condition. And then you can see it is very, very consistent, high quality, grammatically correct, just completely human-like writing. Because you can see that the essence is that unicorns were discovered in Andes Mountain. Andes Mountain is like a region, like a geographical region in the South America, right? And you can see that they have scientists named the population after their distinctive Ovis unicorn and yada yada. And Dr. Jorge Perez, a biologist from University of La Paz. La Paz is the capital city of Bolivia, right? So it completely understands the context that the unicorn was found and the Andes Mountain is located in the South America, and the South American names are Jorge Perez is like South American name, Spanish name. Everything is just completely like, on point. It probably is better than most high school students writing, probably. And the names are the model doesn't even confuse names. Once it says Jorge Perez, it sticks to Perez, doesn't say Perez and then like Hernandez some other time. It's always Perez here. So it completely knows what's going on and what it has written so far, because it has a complete masked self-attention that completely goes this way. This word here has access to all the previous words, attending to all the previous words. So it knows what it has written. So when it is what it has written, so it doesn't deviate from the previous context. So that was GPT-2, and then came GPT-3. So GPT-2, great performance for language modeling. Not so much, I mean, interesting zero-shot task performance, but not as good as state-of-the-art. Then 1 year later, OpenAI researchers came up with GPT-3, so language models are few-shot learners, and now it's 100 times larger than GPT-2, because GPT-2 was 1.5 billion, right? And now it's 175 billion, which means that 1750억이죠, 우리나라는. 1750억 개의 파라미터거든. And 96 layers, 12K hidden sizes, 96 attention heads. Context is now 2K rather than 1K. And compared to 7 authors of GPT-2, now it's 31 authors, because GPT-2, probably they could fit GPT-2 into a few GPUs to train, but now GPT-3 is such a large model with 96 layers, they had to come up with a special, engineering technology to train GPT-3 in a parallel fashion, in a distributed manner, because you have to distribute a single model into multiple GPUs, because you can't fit 96 layers of transformers into one GPU. Your VRAM would explode. So you have to distribute them into at least like dozens of GPUs, or maybe hundreds of GPUs. So a lot of engineering effort went in, and then that's why, hence the 31 authors compared to 7 authors. And it is estimated that they spent a lot of money, about 50억에서 100억 정도를 전기세로 썼다라는, so this is like per training for electricity bill. Right? So it's basically as a very power hungry model. I mean, think about training 96 layers of transformer. You need a lot of electricity, right? So I think, yeah, a lot of people estimate that they spend at least $55 million to $10 million for electricity bills only. So you can't train this model unless you're rich, basically, and unless you have hundreds of GPUs, and the resources just beyond imagination. Before GPT-2, it was 40 gigabytes of internet text from Reddit, right? Now it's 570 gigabytes of text, something called Common Crawl. So Common Crawl is like just basically crawled text from the internet. So it's probably all internet. So all internet, web text, books, Wikipedia. So they just put all the things that you can find on the internet and then dump them into GPT-3, 96 layers of transformer. And then they train it for like probably several months, at least several weeks, and probably a couple of months. And they only do zero shot. They don't fine tune their they don't fine tune their parameter. They can't fine tune their parameter because that would cause this much of money. Fine tuning costs money now. If you think about how much money went into training the original GPT-3, fine tuning GPT-3 would also cause significant amount of money. So they don't fine tune anymore. They just do zero shot, but they have complete zero shot without showing any examples, or showing one example, or showing several examples, like n times, like before. And then actually they don't do like English equals French n times. They actually they order what to do. For example, translate English to French and then just go French, and then what is the French corresponding word for cheese? That's basically zero shot. One shot is they tell the same thing. I want you to do this, translate English to French, and then show one example and then go. And this is a few examples, few shot. So again, order, do this, and then show 3 examples and then go. So they have 3 different modes: zero shot, one shot, and few shot, and they do a bunch of different tasks. And you can see that as they increase the parameter of the model all the way to 175 billion, the performance increases without end. It doesn't. There's no diminishing return. It doesn't go like this. It actually keeps increasing, which means that there's we haven't really reached the upper bound of the model capacity return, because we're here at 75B. But if we went to like 300B, it would still increase. If we went to 500B, probably increase. So like, when does it end? When do we have a diminishing return like this? Like, when is like enough? Like, nobody really knows. But 175B is already too much, because only a few companies in the world can actually train this large model. Like in Korea, it's only Naver and Kakao, I think. Maybe LG and Samsung. I'm not sure if Samsung is doing it now, but at least Naver did it with something called Korean GPT. Right. So average performance across 42 different benchmark data sets, and increasing, always on the rise, always on the rise. So it's worth the money, actually. Yeah. So some interesting examples. Question answering on I think, yeah, trivia QA, WebQS, and natural QS. I think they're all open domain questions. They're all open domain questions. They're not like squad. They don't give you a passage. You have to find the passage. But interestingly, GPT doesn't need to find the passage because it has read the entire internet, and then the parameter, the 175 billion parameters, contain the internet. So it can answer the question, like common sense questions, like, like when it's raining, what do you need? An umbrella. Or when you're sick, where do you go? Hospital. That kind of question can easily GPT-3 can answer. And with few shot, it is as good as the previous Facebook's model, RAG, 68 versus 71, 45 versus 41. Here, not so much, 44 versus 29. But at least if you give enough number examples, like few number examples, it'll show a very, very good performance. Translation as well. So this is the state-of-the-art supervised model, and compared to like especially some specific language pairs. I think this is Romanian or Russian. I'm not really sure. Could be Russian, so I'm going to call them. So Russian to English, state-of-the-art is 39.9. Few shot example 39.9, and here as well. So this is Deutschland. So this is German to English, 40.2, 40.6. French to English 35.0, 39.2. So even without training the model for translation purposes, it is just showing phenomenally good performance. And why? Because GPT-3 has seen the entire internet, and the internet contains French, German, Russian, whatever, Spanish, Italian, whatever. It just in the internet, because it's it has been training on Common Crawl, the entire internet, so it has seen all the language in the world. Right. Machine reading, MRC, machine reading comprehension. So this is kind of like the more classical squad type of question answering. Here's squad, and it is not as good as the state-of-the-art because fine-tuned SOTA is like 93, but GPT-3 can do 69. But again, not sure how they perform zero shot with squad, because in squad you have a passage and a question, so you need to put both into the model to answer the question, right? So I'm not sure how they did it with GPT-3. They probably just concatenated this here and then tried to find the answer pair here somehow. Yeah. Right. And the super glue benchmark. So super glue is like advanced glue. Glue consisted of 8 tasks, right? So super glue has probably more tasks with more complex linguistically involved tasks. So more difficult language understanding tasks than glue. And you can see that the human fine-tuned SOTA is way up here, like almost 90. Human is 90, fine-tuned SOTA is almost 90. And you can see that few shot here giving 32 examples as the few shot example. It is at least it's outperforming BERT, fine-tuned BERT. So you can see how amazing this is. And again here, in context learning for superglue, fine-tuned SOTA is here, and GPT-3. I think this is how many number of samples? Yeah, number of examples. So 32 is the max. If you only show like 8 examples, it's already as good as fine-tuned BERT, And if you just give 32 examples, there's clearly a diminishing return. After you give like 8 examples or so, then all the others is like irrelevant. Probably doesn't really help. But zero shot, not so much. 1 dramatic increase, and then all the way to 8, you get some increase, and then after that is diminishing return. Right. So can humans? This is another just qualitative task. They ask GPT-3, or actually a bunch of different GPT models, like bunch of different GPT models with different sizes. They ask the models to generate a fake text, and then they give this to humans and ask humans whether it seems fake or not. So it's like humans serving the role as a discriminator in the GAN architecture. So humans are the discriminator. And when it comes to GPT-3, this is the mean accuracy, which means that it's like the Nash equilibrium in the GAN, because in the GAN, when discriminator reaches 50% accuracy, it means that it has reached Nash equilibrium, right? Kind of like similar here. It's basically random guessing. 50% of the time, humans say that this is fake and this is not. And 50% means that random guessing because it's binary classification, right? So it means that GPT-3's writing capacity is so good that people cannot distinguish, right? And more increasingly, people just say, I don't know. So this is a very good example of how good GPT-3 can write. Compared to, I mean, GPT-2 already had a pretty good writing ability, if you remember the unicorn example in the Andes mountain. Here, this is the title, this is a subtitle. If you read it, it's just on point. Like Methodist history, we already seen this in the very first introduction lecture, right? The historical split over gay marriage, and then you can see all the relevant words like LGBTQ, you know, all these like it's kind of like internet words. You can see that it is everything is just on point to so consistent, grammatically correct, just very convincing. You know, it's just state of the art. And text, this is the text most confused by humans. So only 12% of people thought this was fake. I'm sorry, only 12% of people correctly identified this being fake, and 88% thought that this was written by humans. And this is the text most recognized by humans. So 61% correctly identified this as fake, and 39% thought this was written by humans. And probably there's a reason, but I won't go into detail. If you're interested, you can read them later. And this is, again, another example that I showed you guys in the very first lecture. Is trying to make the GPT-2 play a game that has not been trained for, which is use it in a sentence. So it's basically defining a unexisting word such as watpu. Watpu doesn't exist in the English dictionary. You define it as a small furry animal native to Tanzania, and then you can use it in a sentence like this. We were traveling in Africa. We saw these very cute watpus, and then now it's GPT-3's turn to play the game. So it's only one shot. Well, you've only shown one example. Fardoddle, which doesn't exist in the English dictionary, fardoddle is to jump up and down really fast. And then the way you use it in a sentence is this. Or actually, this is how GPT-3 thought to use in a sentence. So use it in a sentence, and then the GPT-3 you start sampling from the GPT-3 model, and then this is what you get. One day when I was playing tag with my little sister, she got really excited, and she started doing these crazy fardoddles. So exactly in context. Fardoddle means jump up and down really fast, and you know, after playing tag, 그러니까 술래잡기 하다 흥분해가지고 막 이렇게 날뛰었다는 얘기니까 정확하게 맞게 사용 용례가 정확하게 맞죠. 여기도 뭐 얄루발루도 제가 얘기했듯이 이게 이제 그 어떤 베지터블인데, 이제 호박 닮은 베지터블인데 너가 한번 문장을 써봐라 했더니 이제 GPT가 이렇게 쓴 겁니다. 그래서 내가 이제 아프리카로 여행을 하던 중에 얄루발루라는 그 야채를 먹었는데, 근데 이제 아니죠, 이제 그 정원에서 기른 얄루발루라는 야채를 먹었는데 굉장히 맛있었다. 그러니까 아주 그 시키는 대로 잘하고 있죠, 그냥. 그러니까 이런 게임을 한 번도 GPT는 해본 적이 없을 텐데, 트레이닝할 때는 그냥 사람이 시키는 거를 그대로 알아서 너무 잘 알아서 이해를 하면서 하고 있죠. 이 정도의 능력이 있다라고 보시면 되겠습니다. So this is another example. And if you go to the GPT-3 website, you can see a bunch of different things that GPT-3 can do. It can write promo copies, advertisement copies. It can write codes. It can write SQL codes. It can write Python codes. It can summarize. It can do translation. It can do basically just, you know, any task that you can think of, linguistic tasks, it can do. It can, it can answer questions. It can convert statements to questions. It can convert questions to statements. It can extract words. It can extract nouns. Whatever you can think of, it can do to a pretty good degree. It's not perfect, but it understands what you want it to do with enough number of samples, like enough number of prompts given to it. So these days, there's another research going on that tries to find the best prompt that you can give to the GPT-3 to make it work better make it work better, basically. Because if you wanted to do like translation, then, or if you wanted to do some weird task, you have to give a very, very good prompt, very good, nice example so that it understands what to do. So prompting is another research direction using like large language models like GPT-3. All right, before we end, actually, I'm going a bit overboard again. Sorry about that. So this is the last slide. So open source efforts, because as I said, GPT-3 is such a large model. Ordinary academic organizations like schools or small companies, or small schools, they can't train GPT-3. They can't even run GPT-3 with only like 1 or 2 GPU cards, because GPT-3 was trained on hundreds of GPUs and spending hundreds of like millions and millions of millions of dollars for electricity bills. So it's kind of exclusive to a very select people, and that's kind of going against the open source research effort. So people started to try to open source GPT-3 like models, completely open, so that researchers can equally get access to this large language models. And this is being led by a working group called Big Science. So Big Science is like a loosely organized group trying to open source large language models, starting to create, study, share large language models with AI or NLP research communities. And it started by Hugging Face. Everybody probably already knows Hugging Face by now. So started by Hugging Face and GNCI Idris, which are both, I think, French government-related research organizations. So either one of these two are actually high performance computing centers. They rent out high performance computers like HPCs to researchers who need them, like weather forecasters or like molecule simulator researchers and that kind of stuff. So Hugging Face and these two organizations actually came together with a bunch of Europe-based researchers, especially French researchers in French universities like Sorbonne universities. They came together and then they initiated this Big Science movement, and then they tried to replicate GPT-3 with the help from the French government, or I'm not sure exactly French government, but mostly French government, because these two organizations were involved, these two institutes were involved, and they released so far 2 models: T0PP, which is T0++, and Bloom. So T0++ is a specialized zero-shot task model with 16 times smaller params than GPT-3. So it's a zero-shot, specifically zero-shot model, but it has way more efficient inner working mechanism. So it's way smaller than GPT-3, and you can probably run T0PP with like 1 or 2 GPUs. And they also open source Bloom, which is exactly like the alternative to GPT-3. It's a 176 billion parameter language model, and it is trained to replicate GPT-3, and it is completely open. The checkpoints, the training data, the models, everything, the source code, everything is completely open. So as long as you have enough computer, you can just download them and then fine-tune them or reinforce them, whatever you want. And yeah, they also release datasets. So it's a pretty big effort, and a lot of props to Big Science. And this is a very interesting read. If you're interested in how these large language models like Bloom or GPT-3 are actually trained, I recommend that you read this article here. And this is basically what you need. So Bloom, the mission is to provide a free LLM for everyone, and more than 1,000 AI researchers were involved in making this happen, like at least 1,000 AI researchers. And the training was done for about 3.5 months. So about how many days? Like 100 days. So the whole Bloom was trained for 100 days, and you can imagine the electricity bill that was spent on training this. And I heard that this was backed up by like nuclear electric generator from the French government. And following hardware was used. So you need this to train Bloom, which means that you need about 400 NVIDIA 800 GPUs, which means that you need 48 server models, and CPUs like this, memories, GPU memories, internode connector, and all these. Like, so basically, you need like state of the art computer infrastructure to train Bloom, and you still need 3.5 months to train it. And the checkpoints are here. It requires 2.3 terabytes of memory, only for the parameters. So you can't load them on 1 GPU. You need how many GPUs? You need, I don't know. Your single GPU can contain about 48 gigabytes of, your single GPU has 48 gigabytes of VRAM, right? So you need at least, I don't know, like 50 GPUs or so to load them. And the data sets are 46 languages and 1.5 terabytes. So before, GPT-3 was trained on 500 something gigabytes of data. Now, yeah, Bloom is trained on 1.5 terabytes of data, 46 languages, and total bulk vocab size is 250K. And yeah, the full details is you can just read the full details here. Very, very interesting read. It includes all the how to parallelly train them, how to optimize them, how to do a bit manipulation. All those things are very, very detailed, described here. So definitely worth a read. All right, so this is the end of class. Sorry for spending 10 more minutes. Before I end the class, are there any questions regarding GPT-2 or 3 or Bloom for that matter? This Thursday you won't be able to train. Well, it'll be about BERT, but you won't be able to train BERT from scratch. So you will be able to implement how to train BERT with mask language modeling, and then actually run it a few times, and then try to see what happens. So that would be the Thursday material. All right, before I end, any question? Right. Cool. If you do have questions, always use Classroom. And I'll see you guys next Tuesday. All right, thank you guys. Bye-bye.